Hi, welcome back to episode 3 of the System Design series. My name is Gigi. This is the System Design interview prep series where we just deep dive into different topics to make us better engineers and also to improve our interview skills. So in last week's video, we talked all about databases. We talked about how a database stores data on disk and how it efficiently queries it using indexes and in-memory structures. But today we're going to be talking about a key component of pretty much all highly scalable distributed systems, which is database replication. Replication is exactly what it sounds like, having multiple copies of the same piece of data on different nodes. When we're designing highly scalable systems, this is beneficial for a few reasons. Scalability is probably the number one way it could help us. If we have multiple nodes that are able to serve requests, it allows us to increase our read and write throughput. Second is fault tolerance, so we don't have a single point of failure. So say part of our system goes down, we still have another part of our system that's able to serve requests to our users. And then finally is performance. So let's think of an app like YouTube, for example, where we have users located across the globe. We want to serve that user's requests out of a node that is geographically close to them. This will overall reduce their request latency. So there's 3 different types of replication strategies that we're going to be going over today. The first is going to be called single leader replication. The second is called multi-leader replication, and the third is called leaderless replication. Before we go into each of these, let's just go over a few key terms. So first we have the concept of replicas, which are the nodes that actually store these copies of the data. We have what's called a leader, which is the main node that takes all the write queries from the users. And then we have the concept of followers, which is pretty much the opposite of a leader. The leader node can both take reads and writes, but the follower nodes cannot take any writes. It can only take reads. So our first type of replication strategy that we have is called single leader replication. And in this strategy, we have one leader node that takes all the writes and then a bunch of follower nodes that take all the reads. So the request flow looks something like this. First, a user sends a write request. The leader node writes that to its local storage. Then that change is propagated to the follower nodes. And that change is written to the replication log, which it keeps track of all the updates that happen to the database. So that follower then reads its replication log and makes any changes that it needs to the copy of the data that it has. So the steps that happen after the leader node sends those changes to the follower nodes depends on the type of strategy that you use. Asynchronous versus synchronous replication. So in synchronous replication, when the leader node sends a write to the follower node, it waits for the follower node to return an ACK before returning a success message to the user. We know that when a user then goes to read that data, it will be receiving the most up-to-date copy of the data. And we also know that since that data has been written to at least one follower replica, we know that if anything happens and the system crashes, that we can actually fail over to that follower replica and use that as a new leader, and no data will be lost. So the downside to this approach is that it's very slow. We need to wait for it to act before returning success message to the user. Also, what happens if this read replica goes down? Now we're going to be blocked on that write, and no user's request will be served until that read replica is back up. Now the other option is asynchronous replication. And in this scenario, the leader node actually returns a success message immediately to the user as long as that data is written to its own local storage. It doesn't wait for an ACK from any of its follower nodes. So this strategy is obviously a lot faster because we don't need to wait for that ACK. Now the downside here is that it's more prone to data loss. So now if that main write replica goes down before we have the time to replicate that data to the follower node, then that data could potentially be lost. So because asynchronous replication has a lot lower latency and allows us to be more highly available, it's the one that's most commonly used. Something like synchronous replication might be needed in systems that require a lot of strong consistency. So think like banking apps, so any financial applications. But for the most part, in these large scale systems, you're going to be wanting to go with asynchronous replication. Okay, so now that we talked about single leader replication, let's move on to our next type of replication, which is called multi-leader replication. And this solves some of the pitfalls that single leader replication has of being limited when it comes to our write throughput because we only have one single leader that can take writes. And then also we have a single point of failure. Say that write replica goes down, we still need a little bit of time for that failover to happen. So having multiple leaders can make our system a little bit more available. And then one more benefit is the fact that if we do have multiple write replicas, we have the opportunity to distribute these write replicas in a more optimal way that is closer to our users. Okay, so although multi-leader replication seems to have all these benefits, it actually does add some complexity. So let's say we have 2 users that are trying to update the same piece of data at the same time, but the requests get sent to 2 different write replicas. So when it comes to conflict resolution, we have a few options here. So one option may be to avoid these conflicts entirely by routing requests for a specific user, a specific row to a certain replica. So another strategy we could apply is called the last write wins approach. In this case, we can apply some kind of ordering to these writes. So either based on timestamp or a unique increasing ID. so that whichever one is the later one is the one that's going to be the winner. Or you can just let your application handle whatever conflict it is. So for example, think of something like Google Docs, where we have a shared Google Doc if two users modify the same word at the same time, right? There could be a little pop-up that prompts you to choose the correct version of whatever you're editing. So the final type of replication that we have is called leaderless replication. And it's exactly what it sounds like. There's no concept of leader. Any replica can receive reads and writes. So in order to handle conflicts here, there's a concept called quorum. Quorum just means a majority vote. In order for a read to be considered valid, a predefined majority of the replicas need to agree on the value. And same with a write. In order for a write to be considered successful, a predetermined majority of the replicas need to have deemed that write as successful. So now this formula actually involves a little bit of math. So let's go over a few examples so you can get the idea. If you take a look at the top right corner of this diagram, you'll see a formula. R plus W is greater than N. In this formula, N is the total number of replicas, W is the number of successful writes required, and R is the total number of successful reads required. So let's take a look at this example. In this scenario, we have a user making a write request. This write request is sent to all 4 replicas. So taking a look at this example, we have N equals 4, meaning there are 4 replicas storing the data, W equals 3, meaning a write is considered successful if at least 3 of these replicas acknowledge it, and R equals 2, meaning a read is successful if at least 2 replicas respond with the data. According to our formula, we have 3 plus 2, which is 5, is greater than 4. So this setup ensures strong consistency, meaning when a user goes to make a read, it will see the latest committed write. So the pros of this configuration is that we have strong consistency, and we also can handle up to a failure of 1 read replica before the writes start failing. The con is that the write latency will be higher because 3 out of 4 replicas must acknowledge the writes. Now let's do this next example. We have W equal to 1 and R equal to 1. According to our formula, 1 plus 1 equals 2, which is not greater than N. So this setup does not ensure strong consistency because the reads and writes don't overlap across multiple replicas. So a user may write to one replica, but if a read goes to another replica which hasn't received the update yet, it will return stale data. So based on these values, we can see that this setup prioritizes availability and low latency over consistency. Okay, so I know that was a lot of information, so let's just end this video with a summary so we know in what situation we need to be picking which type of replication. So when it comes to choosing between synchronous and asynchronous replication, if your application requires strong consistency, go for synchronous. If not, go for asynchronous. If you have a read-heavy workload, you're going to want to choose a setup that has multiple read replicas. If you're looking at a write-heavy workload, you're going to want to choose one that has multiple leaders. For a low-latency global service, a multi-region setup will be beneficial to you, ideally with multiple read replicas located closer to the user. And then finally, if you're looking for something with high availability, you can go with the multi-leader or leaderless model. Okay, guys, we made it through another lesson. If you liked this video and you found it helpful, give me a like, give me a comment. I would love to hear about it. And also subscribe for a new video every week. And I'll see you next time.